Swayam Prabha. Digital India. Educated India.
We have now spent a lot of time discussing circuit analysis, but there was something missing in those circuits, some important elements like capacitors and inductors. Okay. So everything we did so far was analysis of memoryless circuits, meaning you don't have either capacitors or inductors. If you don't have that, if you have only resistors and linear control sources and so on, any branch quantity at any instant in a circuit depends only on the inputs at that instant. Okay, the history is not required. It's required only for capacitors and inductors, right? Because the capacitor voltage is the integral of current up to that time. So what happened to current previously affects the voltage at this time. Similarly, the inductor current is dependent on inductor voltage across history up to that instant. Okay. So those are circuits with memory, and to analyze that we have to go through solving differential equations. Okay. So far everything we did was algebraic equations, and sometimes they look complicated, but they were in terms of matrices, and after all they are still algebraic equations. Okay. So what we'll do for the next few classes is to discuss these circuits with capacitors or inductors. Now we won't deal with differential equations in the same general way that if you take a mathematics course in differential equations, that will be in a different manner. Okay. There the focus will be on solving like many different types of differential equations. For us, the very simplest type of differential equation will do. Okay, we'll only be looking at first and second order, and from there you can kind of generalize to higher order. But we'll look at those things in quite a lot of detail because we want to get some insights into the behavior of circuits. Okay. What's the voltage here? Vs R2 by R1 plus R2, and this Vs could have any arbitrary shape with respect to time, and that will simply become that Vs of t times the same ratio, right? What is it in this case? How would you tell? First of all, if I have this arbitrary Vs of t, it becomes quite difficult. Okay, so first we'll start with constant Vs. Constant with time, which is also referred to as DC. I think you're familiar with this term. It stands for direct current actually, but it's quite common to say DC voltage or DC current, although that's redundant. Okay, so what it means is that that quantity is constant with time, and the counterpart is alternating current, which varies with time in some specific way. Okay, so in general the input can vary in any way, right? Any possible way. So let me remove this R1 since there is only one resistor in the circuit. I'll call this R. Okay, so how would we go about solving for this? What do we do first? To solve for any, there's only one answer, right? KCL and KVL. Okay, so this Vs equals the sum of the voltage across the resistor and the voltage across the capacitor. And let's say it's the voltage across the capacitor that I'm interested in. So I will write everything in terms of that variable Vc. Okay. So in that case, what is the current? What is the current through the capacitor? C times the time derivative of Vc, and exactly the same current flows there as well. Okay. So the voltage drop across the resistor is Rc. Okay. What are the dimensions of R times C? Time. It has to be, right? Because you have time here, so that has to cancel with that to give you a voltage. So this has some dimensions of some time, and actually it's a significant quantity as we'll see soon. So what does KVL say now? As usual, I'll put the variables on the left side and the input, which is a constant, on the right side. Okay. So this is what we have, and VC itself is time dependent, although Vs is a constant. Okay. I'm sure you have solved equations of this type. What's the solution to an equation of this type? So we'll look at it in some detail. Okay. Inductors, they work in exactly the same way. So I won't spend a lot of time on this. Okay. Then let me take the familiar one also. We know the differential equation for this VC here. Okay. And here I'll write it for IL. Okay. So this one we know, I'm going to write it right away. This is the voltage across the capacitor, this is the voltage across the resistor, and the total equals Vs. Okay. Now in this case, what do we have? Vs minus ILR, which is the voltage across the inductor, is L times dIL by dt. Okay. So if I rearrange this, I get L by R time derivative of IL plus IL equals Vs by R. Now you can see that the differential equations are exactly the same in the RL circuit and the RC circuit. The coefficients are of course different, they are dependent on the specific components, but the equations themselves are the same, which means that the solutions will be also the same. Okay. So what I will do is discuss the RC circuit in great detail, and the solutions for the RL circuit can be obtained by comparing the terms to that of the RC circuit. Okay. So first we'll try to do it with, even easier case, with Vs equal to 0. Okay. So essentially we'll try to solve for this circuit. This is, I have set Vs to 0 and I have R and C. So what happens to this voltage, right? That's the question. Now, of course, if that voltage were initially 0, then clearly nothing will happen because there is 0 current through the resistor and 0 current through the capacitor, no change at all. Okay. So if I have VC being 0 forever is a possible solution. Okay. But let's say VC initially was some other value. If VC were to be some other value, then what happens? There are many ways we can think about this. First, let's say this was some 5 volts or something. Okay. And I will define I like this, IC also versus time. What is the initial value of IC? It has to satisfy KVL, right? What is it? Minus 5 volts by R. Okay, so it will start from some negative value. Okay, so that means that what happens to VC initially? It has to fall, right? Because IC, the way I have written it, is negative. So current is flowing upward through the capacitor. So that means that the capacitor voltage will have to fall. Okay, what's the rate of change of capacitor voltage? It's IC by C, right? So it will start falling. I will show a kind of segment just to show that. What will be the slope there? Initially, it will be 5 volts by RC. Okay, but of course it won't go in a straight line like that, because as soon as it drops, what happens to the current? The current itself is related to the voltage, but as this voltage drops, as this voltage falls, the magnitude of the current decreases. Okay, so it's still negative current, but of a smaller magnitude. So what happens to the slope here? Slope will decrease. Okay, so it will start becoming shallower and shallower. Okay, so you can expect that it will do something of that sort. Okay, as the voltage across the capacitor decreases, the current through it also decreases. So the rate of change of voltage goes on decreasing. Okay, so that's what gives you a curve of this type. So graphically, you could, even without having heard of derivatives or differential equations, you could have got this curve, right? And then if you work out for IC, it will also do something of that sort. Okay, so the important thing we can take from here is that the initial voltage is of course 5 volts, and the initial slope is 5 volts by RC for this circuit. Okay.